All right, I think we're going to get started. Good afternoon, everybody. Really happy to see you here. um, this is part of a lecture webinar series of the SaferSim University Transportation Consortium. And this presentation today is from a project that was done at the University of Iowa, here at the National Advanced Driving Simulator. And forgive me if I go through some of the results kind of quick. I have a lot of slides, but if you're interested in reading the report and getting into all the gory details, you can go to the SaferSim website and then look for the name of this project, and you will be able to download the final report. Okay. And I'm going to do my best to leave some time for questions at the end. So this study was about the transfer of control in automated vehicles from highly automated to manual control. And we looked at really several different aspects. Key among them were performance of the transfers and the trust that drivers had in the system. And this was work that was done here at NADS. I was involved. I'm Chris Schwarz, Timothy Brown, John Gaspar, and a graduate student, Clara Kuhn, who we recruited for this project, and she was in the Department of Epidemiology. And I believe has since graduated. Yeah. So why are we looking at transfers of control? Transfers of control can be actually the safety critical events for automated vehicles. Whereas traditional vehicles, we are normally looking at crash causation events. In automated vehicles, we don't exactly know what all the crash causation events are going to be, but we know that transfers of control are critical, and they are segments of time that where the driver can be vulnerable to things that happen. Because not only if something develops that you must respond to, not only do you need to have the reaction time to respond appropriately, but you may not be paying attention. And so if a warning comes up, you may have to completely regain situational awareness from nothing and take control and then respond to the event. At the bottom of the screen, you see a table that kind of breaks down transfers of control from lower levels of automation to higher, higher to lower, and then expected transfers and unexpected transfers. And we're sort of focused in where this red rectangle is, kind of in the expected and a little bit in the unexpected, higher to lower. When a transfer is expected, there may not be a takeover request from the automation, but the driver may simply grab the wheel or press a button or press a pedal in order to take control from the automation. When it's unexpected, then the automation might issue a takeover request, and that takeover request may come a few seconds before an event requires intervention. It may come a few minutes. We issued our takeover requests at least 5 seconds, most of the time 10 seconds ahead of an event. So to put this in context with the overall levels of automation, this chart shows the SAE levels. And we're really interested in level 3 here, conditional driving automation. The reason is this fallback situation. The driver is likely out of the loop. They certainly were, for our study, out of the driving loop. However, the fallback, in case the automation failed or could not handle a situation, goes back to the driver. It doesn't go back to an automation system, which would happen in level 4. In level 4, then the automation would be expected to safely pull over or slow down or do something appropriate. In level 3 and in this study, it was really the driver who needed to take control and respond to a situation if he or she was asked to. So the objectives of our project are listed here, and we're really asking, we asked several questions. We asked some questions about trust in the automation, and how is that affected when you change the reliability or the capability of the automation. So we had 2 levels of capability, and both, each driver was exposed to both of the automation types, and therefore they experienced a change in the reliability over the course of their study drives. When did they choose to begin a transfer of control? How long did it take? How long did it take to return control to the automation after the event? How long did it take the driver to really stabilize the vehicle after a transfer of control and return their attention to the road? Were there any performance decrements associated with transfers? And were there any differences in the gender and age groups, either in their trust or their driving performance? So that's a lot to chew on. And if it feels like, you know, this is kind of a ambitious project, it's because there was an exploratory aspect to this study. Part of the reason for that is it's really the first NADS 1 simulator study that we've done with automated vehicle technology and giving drivers exposure to that. So there was an exploratory nature to it, and we were kind of curious to see what would come out of it. And some of it was inspired by previous work in this area that I'll mention during the talk. And so, all right. We had 5 main events during the drive. 4 of them, 4 of them were events that had to be responded to either by the driver or by the automation, and for the drive to continue. And then the 5th was a normal exiting the highway at the end of the person's drive. So a work zone, missing lane lines, sharp curve. Really, it was an elevated ramp, exit ramp, that had little walls on it. It was a fairly sharp curve, a slow lead vehicle, and then exiting the highway. Now, in the condition that had more capable automation, it did not issue takeover requests for several of these. Rather, it just did what it needed to do, changed lanes or kept on going through the missing lane lines, for instance. And in the slow lead vehicle, it issued a 10-second takeover request, and in the exiting the highway, it issued a 30-second takeover request. In the less capable condition, each event issued takeover requests, and the slow lead vehicle was more critical with only a 5-second warning. There were additional filler events that we added into the drive, and those consisted of a lead vehicle just braking. I'm going to show a video of it real quick, so I won't describe it too much. But the purpose of them was to give the driver exposure to a sort of typical situation that might happen that the automation responds to, and it does it successfully. So it's meant to be sort of a trust building event. We had 20 participants, and we balanced those by the automation, the order that they experienced the automation. Some had the more capable first, followed by the less capable, and others vice versa. So here's an example. It's a video of the work zone event. And as we watch it, you'll see, I don't think you're going to get audio, unfortunately. But you'll see him put away his iPad that he was working on and look up, take back control to navigate the work zone. And he did that in response to a takeover request. You'll see he pushed a button with his right thumb, and that was one of the main ways to do transfers of control. He could have also pressed the brake pedal. Here's the work zone. Now he's giving control back to the automation. And now he's comfortable and he's picking up his iPad and going back to the task he was doing. Now here's an example of the filler event I was describing to you. As we watch this, just notice that he looks up because what he's noticing is his vehicle is slowing down and he's getting the motion cue. And so this is one of the reasons that that I would assert that doing this in a motion-based simulator is really necessary to get the cues that are involved, because you can see he's not paying attention to the environment at all. So the only thing that alerts him that anything is going on unusual is that his vehicle is slowing down and he's getting an acceleration cue. And he looks, tries to figure out what's going on. The lead vehicle is slowing down and his vehicle is slowing down. We should put something on these videos like they have in side view mirrors when it says that objects in the mirror are closer than they appear, because it works the same way when you watch these videos. When you're in the simulator experiencing it, those cars look a lot closer than they do in the video. Okay, takeover requests. You can see there's that display that's in the high heads up position. And that's showing an automated mode icon in blue. And then there were three types of takeover requests: an informational warning, a cautionary alert, and imminent alert. And these were adapted from the work done at VTTI on the level 2 and level 3 automated driving. And they had takeover requests that were very, very similar to this. And they also lasted about 10 seconds. And the last event for the exit ramp, you would stack these together. So first you would get the informational, then you would get the cautionary, then you would get the imminent. And here's an example of of a takeover request, of a imminent. And then this one on the right is the reminder cue. It's an audio cue that they received to remind them to give control back to the automation after the event was done. So if they had not already given back control, then that cue would remind them to do so. All right. The apparatus was the NADS 1. If you're not familiar, it's a large motion-based full motion simulator with a full vehicle cab in it, 360-degree surround visuals. The motion base is about 20 meters by 20 meters. So you're really able to do some good turning and braking in it. As well, it has vertical vibration. We developed software in-house to do automated driving control that it was capable of doing lane changes, exiting highways, merging onto highways, doing turns, slowing down at a stop line. And you've already seen how we did transfer of control. We had that button on the steering wheel, and you could press the brake pedal. The task was a trivia game that they could access from the iPad. And they had a choice to do any category they wanted. So, the hope was that the level of interest in the task was similar across the subject pool. And the task itself, of course, was fixed. So we really wanted to try to standardize the level of engagement and workload as much as we could. It's important to realize that this is not a secondary task for these drivers. Once they put the car into automated mode, it becomes their primary task. And paying attention to the road is then a distraction to them. Okay, some of the measures and analysis techniques that we used in this study. Our independent measures were the order in which we presented the two types of automation. They had two study drives or two scenarios that they experienced. And each one had the same events in different orders, and it had a different capability of automation. And as well, we controlled for gender and age. And then we looked at several dependent measures, including the duration of the event and how long they spent in manual control, response times for them to take over, take back control, and then give back to the automation the control. We looked at their gaze and measured the PRC, the percent road-centered gaze, which is just the percentage of time they spent looking at the road. We collected in the cab, as part of the simulator data, trust measures from a Likert survey that was on a screen in the cab, and I'll show you what that looked like in a minute. And then we had post-drive survey responses as well. Now, in addition to those dependent measures, we defined what I'm calling longitudinal measures. So these were measures that we defined in a 5-second period for up to 12 segments after a takeover. And these were adapted from work that was done at Leeds, and they did the same type of thing. So you're able to see the evolution of some of these variables over time after the takeover. We looked at speed, steering reversals, SDLP, high frequency steering, and the PRC gaze. And then we also looked at the PRC gaze after they gave control back to the automation. So we were able to see how quickly drivers went back to their trivia task. We used SAS to analyze the post-drive survey data. We used R for everything else that was in the simulator data. We ran ANOVAs for several of these, applying Box-Cox transformations where appropriate to achieve a normal distribution of the residuals. And then we made extensive use of linear mixed effects regression. And we used the LME4 package in R, which was really great. And the interesting thing that we did was when you use time as a factor in the mixed effects regression, then you get what's known as a growth curve analysis. And you can do some really clever things, treating time linearly or quadratically or polynomial. And I'll show you in the results. We'll get to what you actually see when you do that. In terms of accuracy measures on the linear mixed effects regression, well, the relative accuracy is traditionally done by something like an AIC or a BIC, and we reported both of those in the report. Absolute accuracy, you might normally turn to p-values, but LME4 toolbox doesn't report p-values, which may be problematic to some people. Instead, I used another approach that is documented in the report. Right? You can estimate marginal R-squared values that explain the fixed effects, and then conditional R-squared values that explain the combination of the fixed and random effects. So that's what's reported in the results. But don't worry, I'm not going to show you tables and tables of numbers today. So here's some results on trust, and this is, I'm going to show you a little video of the Likert survey. I'm going to try. There we go. So you can see that survey was placed near the center console. It is not that high. So really, if they're involved in their trivia task while they're doing this, there's no need to even look up at the road. They can just glance over at the screen, press their response, and go back to what they were doing. Now, we had a practice drive that had 2 of these, and then there were 8 and 8. Yeah, there were 8 in each main drive. So a total of 18 instances of this Likert probe were administered, and then we used the log of the raw Likert score as our main trust measure. And so you can see color-coded the practice drive, the A drive, the first drive, and the second drive. In some cases, the first drive was the more capable automation. In some cases, the first drive was the less capable automation. In doing a cluster analysis on linear mixed effects regression fit to these comfort profiles, we were able to tease out 3 groups or 3 clusters of types of the evolution of comfort that people had. And in the red color is cluster number 1, and in that one you can see that that comfort increased as the number goes down. That means comfort is increasing. So comfort increased gradually and fairly consistently throughout their time in the simulator. The second cluster was fairly level, and people started out fairly comfortable or wherever they were, and they kind of stayed there. Maybe went up and down a little bit. Maybe there were a couple interesting cases that had spikes in them, but generally cluster 2 was pretty level. And then cluster 3, you started out with less comfort, and then you spent some time acclimating yourself to the system, becoming more comfortable, and then they reached pretty much, their maximum. They're very, very comfortable where they remain for the rest of the drive. In the post-drive survey, we didn't observe any significant effects. This is an example of a question that was asked on that survey. How comfortable did you feel when the automation failed and you had to regain control? It looks like there could be some trends in there, but there was nothing that came out statistically significant. So let me give you some results on takeovers. We looked at different phases or different aspects of manual takeovers. Phases might be the wrong word to use, because really when you think about the ones expressed in this table, they overlap one another. The first one is physically taking control by pressing the button, for instance. How long does that take after a takeover request is issued? Second is physically stabilizing the control of the vehicle after taking control. And third is visually attending to the dynamic driving task, and we measured that with our gaze. And the fourth, to kind of put it all together, is when is the driver regaining full situational awareness of their surroundings and driving completely normally. And I would submit that that's really a very complicated question. And so I don't think any of our dependent measures is giving us a full handle on that question. But it's one of the things that we would be interested in looking at further. So phase one is physically taking over. There's a distribution, of course, but the average takeover time was around 4 seconds in the four main study events, and then on event 5 we have this trimodal distribution. And recall that we actually had 3 different alerts that were stacked, and this type of result was also seen in the Virginia Tech work. It was thought in that work that perhaps one of the reasons that people were waiting into the second stage was that their takeover request actually had a countdown where it would count down, you know, literally to the time of the next stage. And ours did not, but we still have this trimodal distribution here. It's kind of interesting. This also echoes, I think, previous work that was done that shows that people can take over really fairly quickly. And if there were a safety critical event that they really had to respond to, people could probably take over even faster. But looking at phase 2, where people then have to take control of the vehicle and stabilize it, we looked at SDLP and this high frequency steering measure. And the interesting thing here is that you can see in the first 6 segments of time, this is a longitudinal measure. So each instance at the bottom is a 5-second period of time. Can you give me some water? And this is showing that really for about 30 seconds, and this is aggregated across all subjects. So, you know, you're going to see individual differences, but really for about up to the first 30 seconds after you take back control, the standard error was quite a bit broader. And I think that's kind of interesting. And then takeover phase 3 had to do with visual attention and the percent road center gaze. And what actually happened is that some people's gaze never really returned to normal after a manual takeover. So we fit a line to the trend as it was increasing and extrapolated if we needed to find the time that PRC would reach 70%, which is about in the normal range. PRC, if it goes too high, like 85, 90%, then you're actually in the range where we associate that with some cognitive distraction, gaze concentration. So 70% is about right. And so we're seeing some numbers that go, you know, up to 20, even up to 40 seconds. There was a result here where we can see that younger drivers took significantly less time to return their gaze to the road. So they were able to switch their context more quickly from the task back to the driving. And then returning back to automated mode, we did exactly the same thing, only we were looking for the time it took the PRC to drop to 10%. And here again, younger drivers took much less time to switch back from driving to the trivia task. And interestingly, older females took the longest to reallocate their attention, but only on the first drive. They adapted after that. And in their second drive, they took much less time. I'm going to spend the remainder of the results slides on focusing on the lead vehicle event. In the report, you'll also find some results on some of the other events, but I think the remarkable thing is that the lead vehicle event really had quite a few results associated with it. Perhaps because it was maybe the closest thing we had to a safety critical event, where you were coming up on this truck that was driving at about 25 miles an hour. And it was the one where, in the less capable condition, we issued only a 5-second takeover request. So, first of all, time spent in manual mode. This is the time from when they took back control to the time that they gave control back to the automation. In the condition with the less capable automation, so that would be the one where they had the 5-second takeover request. There was a difference in age, and there was also a difference in gender that we saw. Younger drivers spent much less time in manual mode than the older age group. I say older, but it's 25 to 55, so I'm getting up on the high end of that. Men spent less time in manual mode than women did. So some of the interesting results that we got out of this study really had to do with gender and age differences. Minimum speed. This is the first slide that shows some of the results from the linear mixed effects regression. So let me take just a moment to explain what's going on. On the left, you're seeing a caterpillar plot that shows confidence intervals associated with each term of the mixed effects regression. So if it were purely a linear fit, there would be an intercept and a slope, basically. But this was a little bit more complicated. I believe I did polynomial time for all of these, so time itself could have a linear component and a quadratic component. So the fit over on the right, if you look at the red lines with the gray bars as the confidence region about those lines, you're seeing the fixed effects polynomial time, so it can look quadratic or it can look linear. And the differences in those red lines are the differences between the two groups. Back over to the left, what you're looking for is the confidence intervals to be outside of 0 and not include the red line at 0. And if that's the case, then you can surmise some kind of significance. And because we see that with gender, I'm showing the differences between the gender groups on the right. And indeed, you can see that the women had a lower minimum speed, quite a bit lower on average than the men did in that event. Steering reversal rate had possibly barely a significant effect of age, and that's shown on excuse me, shown on the right. And by looking at that, you can see that the younger age group had perhaps a little bit less, fewer steering reversals. SDLP, again, it's the confidence range is close to the 0 line, but doesn't quite cross it. So looking at it, you can see that the older age group had a little bit less SDLP. And then this event, or this result, is interesting in that it's focused on the first drive versus the second drive. It's not a result on age or gender. And there were other results like this that I'm not showing you, but you can find them in the report. So this is showing that in the first drive, the the high frequency steering has more of this linear look to it, and perhaps is, well, it's a little hard to tell because you can see that there are a couple of people who might be considered outliers. And if you took those two folks out, then that might make the behavior look about more similar. But on average, there's quite a bit of a difference in how people steered during the first drive as compared to the second drive, which would suggest a change, a link to the change in comfort as they became familiar with the system. So it wasn't necessarily associated with the capability of the automation because some got one and some got the other. And it wasn't necessarily linked to the order that those were presented, just merely by virtue of the fact that they drove, it's their first drive or their second drive. All right, let me conclude and then we can move on to some questions. So, again, excuse me, one moment. We considered trust through the fairly narrow window of comfort because we surmised the comfort would be a good indicator of a driver's nascent trust in a system that was unfamiliar to them, as this system certainly was. The first thing that you have to do is become comfortable with the system as you learn it. Beyond that, then you can start to learn more about the system and its limitations and what you and develop a good mental model of it. But really, I don't think that we gave drivers enough time to do all of that. We did give them enough time, though, to become comfortable with the system. We identified 3 types of comfort profiles. And what we can do now in future work is to start to bring in other dimensions of trust. And some of these have been documented in other work. Things like predictability and performance, or dependability and reliance, faith in the automation, and collaboration with the automation. These are all aspects of trust. So we varied reliability by giving people 2 different capabilities of the automation and having it change on them from the first drive to the second drive. But it was interesting that we don't have many results that show an effect on changing the capability of the automation. We did see some results that show that the first drive is different than the second drive. And so one of the reasons that maybe we didn't see as much of an effect of the changing the capability of the automation was that they weren't all that different. And we didn't put people in truly critical situations either. So, one of the things that we could have done were to introduce more safety critical events. We could have also introduced what I would consider true automation failures. And in a real failure, you would have a situation where you need to intervene, but the automation isn't even on top of things enough to issue a takeover request. And so you have to notice it yourself and take over control. That, to me, would be a real failure of the automation. And it would be a true test of that driver's situational awareness. But we didn't go to that extent in this study. Now, we did see that takeover timing was quite a bit different. There was individual variation that you could see in the distribution, but it varied greatly by phase, where physical takeovers would take about 4 seconds. The high frequency steering would show a period of stabilization after takeovers, and then visual attention would have to return to normal. Now, the concerning thing about all this is that those things happened, those phase 2 and phase 3 happened after the takeover. So the driver had control and then needed to complete the process of regaining their situational awareness. And so that's why one of our conclusions from this work, and it echoes, previous studies that have been done, I think it leads, and there's a window of time after a physical takeover that we would surmise that drivers might be at higher risk because they're still in the process of stabilizing and regaining their situational awareness. So there are several open questions that remain that we would love to take a look at in future research. One would be we've identified this vulnerable window of time after takeovers, but really what's the safety impact of that? Just because I'm showing you that the high frequency steering is greater for up to 30 seconds, what does that mean in terms of safety? The answer is I don't really know yet. How do other dimensions of trust factor into drivers' expectations and about the automation and responses? Why didn't we see more effects of varying the automation capability? And how much would we have had to change it in order to see an effect? I don't know the answer to that right now. And how could we use some of these results to design an automation system that would quickly engender trust, that could perhaps use information from driver monitoring system to design an effective HMI. So there are all kinds of interesting questions. And I have seen some questions flow through the chat, so let me bring up that chat and see if I can address some of those. Do I have to escape?
Yep.
Okay. Okay. Can you define high and low frequency steering? Yes, I will do my best. That measure was also adapted from the Leeds work, the 2014 paper from Natasha. And basically, you're looking at two frequency bands of steering. The low frequency is, oh, I'm not sure if I'll remember the numbers, but it's maybe 0.3 to 0.6 hertz or something. And the high frequency band is 0.6 to 1.5 maybe. Again, I might be wrong on the numbers, but you can use a power spectral density to get the density of steering in each of those bands, and then you take the ratio of high frequency to low frequency. And the idea is that if that high frequency steering measure is larger, then that is an indication that the driver could be distracted in some way. How much time has passed between the first and the second drive in each participant? Not much time, only a couple of minutes, enough time for them to take a couple of surveys, simulator sickness questionnaire, and the trust survey. So maybe 3 to 4 or 5 minutes. Great. Other questions?
Do you think that given that time between the two drives, in the absence of anything on there, you could maybe having people back again, you would have seen some differences in the levels of the capabilities of the automation, that people were growing accustomed to it, and then even with those same two levels, if you had continued more drives, even maybe on another day, you may have seen those. Okay.
Yeah, so the question is, in case you didn't hear it, if we had given more time in between drives, might we expect different results on the trust? And I think the answer is definitely yes, especially if we had split it up into multiple visits and made it more of a longitudinal study, which we did, interestingly enough, 20 years ago for the automated highway system research. We did that type of longitudinal study at the Iowa Driving Simulator. And then you could really go beyond just looking at how long it takes for a driver to get comfortable with the system to how do they start to behave when they are perfectly comfortable and they start to, play with it. And of course, we know that drivers today are learning they're learning every nook and cranny and figuring out how to game their automation almost. It's, like a type of misuse perhaps. But that's you get to that level, when you start to get a good model of how it works and you're comfortable with it. And yeah, I think that we would get further into that regime the more trials we have people drive and the more separation in time between those. It's a good point.
The other thing I wondered about is you said that you had 3 stages of alert. You had people waiting to the second stage
Yeah.
to take over. Do you feel like they attended to the roadway to assess the situation between those 2 alerts, or were they still engaged in the other tasks? And they were simply waiting for the second stage of alert. So were they trying to gauge whether or not they need to take over after the first alert before the second?
Yeah, that's a really good question. And I don't have results, or we didn't look at the PRC, for instance, to see if people started visually attending to the road when they got that first alert. The first alert was an informational takeover request, and the wording of it said, prepare for takeover. So people may have interpreted that as, get ready to do something instead of doing something.
Mm-hmm.
So, but again, I don't know what the data showed as far as did they put away their trivia game at that time, or did they just keep on doing their task until the second or third alert? Okay. I don't know.
No, for anybody else online has any questions?
No?
No?
Anybody else?
Yeah, please tell me. I don't know if they can hear me, but the report is available on the SAFERSIM website. Just Google SAFERSIM and then go to research and find the project.
Yeah. So if you want to download the report, you can go to the SAFERSIM website, go to the research section, and you can download not only our report, but all the completed reports from SAFERSIM projects.
Mm-hmm. And the recording of this webinar will be available on our YouTube channel within a few days.
Great. So this webinar will be available on our YouTube channel in a few days.